Okay, so we have here some wax pellets, right? And so we can see they're in solid form. So based on the previous videos, you should know that the forces between wax molecules, are they strong, weak, or medium? Well, we talked about how if something's solid, that means it has strong intermolecular forces. So there's something holding these wax molecules together. So based on the previous videos, we talked about this concept of polarity, right? So remember, a molecule can have an unequal sharing of electrons, which one electronegative atom can pull electrons to one side, creating a partial small negative charge, which leaves a little bit of positive charge on the other side, right? And so what does this do? Well, it allows these molecules to stick together, right? It's a strong force creating, potentially a liquid or a solid. So we might assume then that wax must have some polarity in it. Let's go ahead and look at the molecules. So these are the wax molecules. And if you remember from the last video, one of the things I said is one of the most common non-polar bonds is CH, okay? This is a really weak electronegativity difference of 0.4. So we consider this to be a non-polar, right? What we said to look out for polarity was O's, maybe NH, right? OH, and things like that. Those are the most common polar bonds. Let's see what we have here. So this is a wax molecule, and notice, oh no, it's all C's and H's. Look, CH, 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 right? So this wax molecule, it's a big molecule, but it only has non-polar bonds in it. And I circled these other two. These are also the exact same chemical as this. They're just different ways to show it. So this is a lot of writing to do. So chemists a lot of times will just draw these line structures. And notice, like the tip here, is this tip here. So this little tip is a CH3. So it's a carbon with 3 hydrogens. This little bend here is this little bend here, right? So that's kind of how these molecules work. So you might see something like this in your biology class. This is kind of the longer version, and then this is what's called the space-filling version. Again, you can see that there's a blue carbon there and then 3 hydrogens representing this section. And so this is kind of showing the electron cloud around this molecule. That's going to be important later. So I want you to see all 3 versions of this. This is the efficient way to write it. This is the long way, and this kind of helps show us this cloud of electrons around this molecule. But this takes us back to the problem. This is a nonpolar molecule, so there's no partial charges that are attracting this molecule to another wax molecule. So how is it sticking together? We know the intermolecular forces are strong because it's a solid. So how is it happening? So there must be some other type of force besides polarity. So that force is London dispersion forces. So this is a little bit weirder than polarity, but basically in a cloud of electrons, what can happen is maybe this is normally how the electrons are, but these electrons are flying around randomly and chaotically. So you can imagine that every once in a while, just by random chance, a lot of the electrons will kind of fly to one side. What will happen is you'll get a temporary polar charge, right? A little bit of negative here where the electrons are meeting up, and then a little bit of positive charge here where they kind of left, right? So you get this kind of temporary, short-lived, polar thing, and then this can create some attraction between other molecules, right? So we can see some random electrons gathering here, attracted to some random electrons being left here. So these London dispersion forces are basically random motions of electrons creating temporary partial charges. These are really weak forces, right? This is weaker than our polar bonds that we talked about in the last video. So here's a definition that you should know. So make sure you know this here. I'd write it down if I were you. So present in all molecules, because all molecules have electron clouds, they're temporary partial charges and they give temporary polarity. So one of the ways to increase this is the squishiness of the electron cloud. And so how do we do that? This is another thing you should write down. Larger molecules have more electron cloud to squish, right? More electron cloud to squish. So the bigger the molecule is, the more of these London dispersion forces it have, right? So, and we can see in a very small molecule here, sorry, we have our helium atoms, right? These are very small atoms, and so they, yes, just like any atom, they do have an electron cloud, so they can kind of randomly move these electrons around, right? You can see they doubled up over here, so there's a little bit of negative charge, right? And then it leaves a little bit of positive here because of the nucleus, and so it might be attracted to another helium. But this is a very small atom, so this is a very, very, very weak force. So helium, of course, is a gas. Let's go back to our wax and just take a look at it real quick. Look at this molecule. This thing's big, right? So this cloud of electrons has a lot of options, a lot of room to kind of squish and make these little bits of partial charge that kind of just pop up randomly. So if you stick this next to another wax molecule that has the same thing, it's going to stick to it, right? So I have a little model here to kind of show what's going on here. So if you've ever seen these little magnetic strips, you probably know these are pretty weak magnets. You can't really put anything too heavy on them, right? So this will kind of simulate our wax molecule. It's a big strip of magnet, but it's a very weak magnet. So if we have another wax molecule, so on this pipe here, right, it's a pretty heavy pipe, I put another strip of magnet. So again, this simulates like a second wax molecule. So again, weak magnet, but there's a lot of it, right? So when I stick it on here, it sticks just fine, right? You know, I can tap it. It stays on there pretty good, right? I can pull it off, but it stays on there pretty good. So even though it's a weak magnet, there's so much of it that all the forces added up together end up being a big, force between them, and things stick together. So this would be like our wax. It's a solid. The forces are weak, but there's so many of them because it's such a big molecule that it can stick together, right? Let's compare this to a smaller molecule, right? Look how much smaller this molecule is. It still has those same forces, but there's less of them. So if I try to stick it to this, oh, yeah, it falls, right? So there's definitely still some attraction there, right? You can kind of see it. It does kind of stick a little bit, but it falls really easily. So this is a smaller molecule, so this would be more likely to be a liquid or maybe even a gas because of how small it is. So that kind of gives you an idea of how these London dispersion forces work, right? So the bigger the molecule, the more of those weak forces add up, and you end up with high intermolecular forces at the end of the day. There's some other famous molecules that act like this are fatty acids or fats or oils, right? So we can look at some saturated fatty acid here, and we see the same structure, right? Just a reminder, this structure is showing this. Now this does have a little bit of polarity here, right? You should recognize that there is a little bit of polarity here, but that's not enough to explain why this molecule looks like this as a solid, right? So saturated fatty acids would be the kind of fats we would see in butter. So big molecule, London dispersion forces are holding these together, creating a solid, right? And we can kind of see the space filling model here for our saturated fatty acids. Notice there's a lot of surface area, so those forces can interact really good. Let's compare that to a saturated fatty acid. Look at the chain here. Look at the carbons and the hydrogens. It's almost exactly the same, right? Look at, if you counted these up, it's pretty much exactly the same. But look at our olive oil. What state of matter is in it? It's a liquid. So the intermolecular forces are weaker than our butter. Remember, the weaker the forces, the more likely you are to be a liquid compared to a solid. So what explains that if it's the same size molecule? Well, notice that it has this little bend in it right here. Notice what this does to the molecule. So it has all those same forces in it that our saturated fats do, but there's not a huge overlap here. There's not a huge overlap. And so those forces don't interact as strongly, and so the forces between the molecules is weaker, explaining why this is a liquid. So going back to my model that I have here, I have that here. So I created a unsaturated fatty acid. So this would be kind of similar to our saturated fatty acids, right? Just a reminder, it sticks really strongly and is a solid. If we look here, this is our kind of mono unsaturated, our olive oil. If I stick that on, okay, it does stick on, but look, a little tap, right? Remember this one I could tap pretty good, right? It's really on there. This is our solid. So that guy there, it did attach, but that small little tap knocked it right off. So the forces between it are much weaker. And that explains why our olive oil is a liquid and our butter is a solid, right? And then olive oil, of course, tends to be the heart healthier one because it keeps your blood a little more liquidy. Butter tends to make it a little more sticky and solid, which is harder on your heart. But again, this goes back to those London dispersion forces. Okay, the bigger the molecule and the more surface area it has, the more those forces are going to add up. So this explains why our nonpolar molecules can sometimes be liquids and solids. It just depends on how big the molecule is.